So, some quick calculus stuff. Okay. So, basically we are always interested in something, the words tangent, gradient. We are interested in the gradient information. Why? The example that we discuss now should tell you why I will be interested in the gradient information. Because gradient tells you what information that gradient says.
Whether it is we have reached maximum.
Okay. So, it gives me this information, the direction of maximum increase. In a 2D problem it was very clear. Okay. Now, imagine you have a hill like that, an optimization problem can be described like that. Okay. This is how an algorithm starts to work in, this is you who is trying to climb this. Okay. So, you can start here, when I say there it could be anywhere here, okay, and assume that you cannot see the, you cannot see, okay, meaning you cannot see means I am blindfolding you, okay, and then you have a stick in your hand, okay, that is the usual example that we give. Okay. So, what you will do is you will look for the maximum increase, because you also want to reach there as fast as you can. Okay. So, what you will do is you will take your stick and you will do like this, and you will find out whether the maximum increase is here, 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 which direction it is. Let us assume that this is where the maximum is. So, you will start going in this direction. Instead of going step by step, you can also jump. So, will you jump for 1 feet, will you jump assuming that you can jump, okay, like how many ever feet it is. Will you jump for half a feet, will you jump for 1 feet, will you jump for 10 feet, because you do not know, right, I have put a valley here. Instead you could take a smaller slope, smaller gradient, and you might be able to reach faster. Okay. So, that is called line search. So, this is the direction in which you need to start, because I blindfold you, I rotate you and I leave you. You use the stick and then you have 360 degrees you can climb, if you can climb. So, and then you find out, okay, so let us even put this slightly differently. So, let us say it is actually a valley kind of a stuff. So, you are inside the valley. Okay. So, you can check all sides and you are free to get on whatever side it is. So, which one will you make a decision? Where there is a increase number 1, and if you have multiple increases, which one will you choose? Okay. If I did not put that valley on one half of or like a semicircle area, it will be going down. So, that tells you like I should not go that side because I want to go to the top of the hill. So, you will select only the other half. In that other half, if you have multiple slopes that are going up, which one will you choose normally? The one, do not ask me, sir, 90 degree can I climb, that is a different thing. The assumption is you can climb. Okay. So, you will take the one that can take you the fastest, that is one. The second is how far do you go in that, that is called line search, that will come. The direction is given by your gradient, but what information does it say? It says it is increasing. Now, just take your hill example outside, represent it as a function. So, as a design point, this green guy who you were is a design point. Okay. The algorithm looks for the design point, which side it should go. So, it will choose the direction of the gradient. Okay. So, that is important. The direction of the the direction of the gradient means it tells you the direction in which the function is increasing. If you are minimizing, you will actually go in the opposite direction. Imagine that you are here, you are at top here. Okay. So, then you want to go to the valley. Okay. So, what will it will say that the function is increasing in this direction. So, you will take the opposite direction because it is supposed to decrease that side, it is very simple. Okay. So, hence you need to have an understanding about a gradient vector. Okay. So, and you know all this, right, it is normal to the tangent plane. So, if I have a surface, there is a tangent, it is normal to the tangent plane, that is one thing. So, just to give you an idea, if this is a circle that we are talking about, okay. So, at this particular point this is the tangent, see the circle can increase in all sides. So, you are talking only specific to this point here, okay. If I had another constraint that is going like this, then it is increasing in this direction. So, these are all more like local quantities. So, oftentimes when you are talking about optimization, you are talking only in the neighborhood of the particular point. So, sometimes global optimization is okay, I mean okay, because it is only in the neighborhood, that is why you get local optimas, okay. So, at this point this is a tangent and this is my gradient vector, okay. So, it is increasing in this point, it is increasing in this direction. If you go to this point, it will increase in this direction, okay. That is something that you need to appreciate. Now, this is a first order business. Obviously, what is the second order? It is d squared f, okay. This is okay. The other one is Hessian. What is this guy called? Gradient is also called as do not use the word slope anymore. You are engineers, they are two graduate engineers. So, use the word gradient, it is more n dimensional, okay. So, the second order partial differentiation is your Hessian matrix, okay. This information is also required. So, what does notionally what does Hessian vector give you? Because this guy we know gradient means what? Gradient means what? What does a gradient mean? Simplest notional understanding of what a gradient is. No, direction is actually we derive it, okay. So, when I say gradient, see people use sometimes while constructing this you know what you call inclusive floors and all that, they say the gradient of this wall is this much. So, it is slope, okay. So, in n dimensional that means slope. So, basically it tells you what the slope is, by how much it is increasing, the rate at which the function is increasing, that is what your gradient information is telling. So, what should the Hessian give? The Hessian should give something more than that. What is that? So, it captures the convexity. So, this guy is the tangent, not tangential information, the tangent based information, right. So, that is slope. So, what the Hessian says is it gives you the second order, the same information, but it gives you a higher order information, okay. So, someone comes to the wants to apply for your department, comes and asks you what the entry criteria is, that is the first order information. If they go and ask your professor, sir what is the entry criteria, that is the second order information. They go and ask your HOD, that is the third level information, okay. So, similar, they all are the same thing, but they give more and more information as you go. So, Hessian gives for the same problem, it gives you a second order information, that order is important, right. So, I want to do a second order. So, this gives, as he pointed out, it is the curvature information that you look at. I guess you guys remember your dou y by dou x equal to 0 from your 12th standard, 10th standard, whenever you studied that, okay. Whenever you want to do minimum maximum, what do? You take a function, you take dou f by dou x equal to 0, that is because that is what the slope is, and then you do dou squared f by dou x squared to find out, because both for minima and maxima that is the same thing, then we will come back to that, okay. So, this is just tells you like if you take a function like this, you want to construct dou f dou squared f. So, this is okay, this is here written, right. So, okay. Now, we will just one step in the side, we will try to talk about something called the Taylor series, and then we will go back and see why this is important in optimization, okay. As the question here, what is the beauty of Taylor series? And you three, maybe you can answer, yeah, you two cannot answer, yeah. Sorry? Taylor series is an approximation. Approximation of what?
It can approximate the neighborhood values.
Okay, fine, very good. It is an approximation of the function. That is a very important point that he said, in the neighborhood, okay. what information does it require? That is where they, because there are a lot of function approximations, but Taylor series is very interesting for optimization for the very fact that he pointed out neighborhood. It is in the immediate neighborhood. I cannot tell you where, what is the function value there. In the immediate neighborhood of where I am standing, I will tell you what the function value is, but I need some information. What is that? You need the, of course, the function value of where I am standing and then the gradient information. You just need to give me these two values and I will give you the function value in the immediate neighborhood. Please understand, it is a very complex function. I do not know how it looks like, or it could be a linear function also, I do not know that. But wherever I am standing, you just need to tell me what that function value is and you need to give me the gradient information, and I will tell you in the immediate neighborhood how my function looks like. This is all is required oftentimes. You do not need to have a overall understanding of what your function is. In the neighborhood is what I need to know what my function value is. That is what your Taylor series does. It is a representation of a function as an infinite sum of terms. The interesting point is, you say why you are stopping only with gradient information, I will give you Hessian information. Good, I can approximate my function even better. So, it is an infinite sum of terms with higher order terms. Okay. So, this is your function value at the new point, this is your old point, gradient information divided by the difference d, second order information divided by d squared. Okay. So, if you would write, you would write it like this, del f d plus, or you can write it as, how can you write this one? That is a quadratic form of writing it. You understood what I have written, right? So, del f means gradient information times d, x minus x star, it is the distance between the point that you want and the actual point where you know the function, that is d, and the square of that is d squared. So, this information f double prime is nothing but your Hessian second order information. So, I can write it as del squared f d squared, but in quadratic sense this del squared f is nothing but your Hessian h, I am just giving the representation h. Okay. And this maybe what is the usual g, Jacobian. You can give, yeah, you can give g or something, but it will confuse here. So, you just keep it as del f only. So, Hessian is h in this particular case, that is all. It is quadratic form d transpose, because this d is a vector, please understand, because I am just writing it as x, but x could be x1, x2, x3, it is in space, there is a point in space, here is a function value, x star, what is the value? So, you have a plain paper, someone? All my, just give me a plain paper, because I have papers, but it is all, no, just 1 second, that is okay, that is okay. This is a nonlinear function. Imagine that this is a nonlinear function. Okay. Now, okay, do not worry. This where you do not need to know, because you cannot see projection, right. So, I am interested in approximating my function value here. Okay. So, this is x1, this is x2. Okay. This guy is x2 and this guy is x1, meaning for you it is x1, this is x1 for you and this is x2. Okay. What I am saying is, any function, any value in this surface is described by f of x1 comma x2. So, if I want to approximate my function value here, where I know the function value here, what I am asking is give me that function value plus what is the gradient information. So, what will be the, I am not asking the elements, but I am asking the number of elements in the gradient vector for this one, right. So, the point that you need to understand why I took this example is because I wrote this one and I told it is a vector, because when I have a point here, it is described by x1 star, x2 star, and I want the value at x, which is x1, x2. I want the function value at, okay, please understand, in this whole point you do not have this function. That is something that you will have to appreciate. For the sake of discussion, I am showing you the function. In reality, you do not have this function. So, when God comes, what will you ask? You say, boss, please give me the f. This is what you told me, right? Earlier you told me, give me the f. You know the f, then it is very easy. You do not even need Taylor series. If you do not have the function, now I told, okay, f value is here. Can you tell me what is the f value here? It could be linear, it could be quadratic, it could be nonlinear like this, it could be anything. How will you know? You cannot interpolate just like that. You will get sacked if you interpolate in this just like that. I gave you 4 values here, interpolate, you are gone. Your interpolation will go like this, the actual function is in the other side. Okay. So, it essentially we are looking at interpolation only, but do not worry, we will correlation, there is a little bit of a correlation with your output function and then you will do it. It is still interpolation only, do not worry, it is not direct interpolation, that is all. Okay. You will not, imagine whenever I show the function, something that you need to record on your mind is you do not have the function, that is the whole point. Okay. Now, if you want to go from point x star to x, okay, then it is basically a direction or it is a distance between the 2 points. So, it is x1 minus x1 star, x2 minus x2 star, that is why it is. Okay. So, it is a vector, that is why I told that d transpose times d, you can write it like that when it is x minus x star squared in a matrix sense. When you write it, it is called the quadratic form. You do not write x minus x star squared, that is for single variable. When it is multi-dimension, you write it like this. So, it is called the quadratic nature, quadratic form. Okay. Okay. So, this figure tells you what happens to the approximation when you use higher order terms. So, let us wait. When you see n equal to 1, you saw that point, right? At that neighborhood it will be correct. Okay. You cannot say, sir, at minus 2 it is a very bad true, it will be a very bad approximation because you have used only one value. The second, it will use your gradient information and it will still be only like this. Then n equal to 3 gets slightly better. When you keep on going in this direction, for n equal to 7 and 8, it gets a very good approximation. Okay. But do I really need an overall approximation? Maybe not, because that is how optimization works. What it says is it looks for the stuff and then it goes to the new point and then it has to evaluate that. So, it is only in the immediate neighborhood that I need to know, okay, because that is what you also did, right? You searched only in the immediate neighborhood. You cannot have an infinite stick and search there, it does not make sense also. So, Taylor's expansion is used widely in optimization, okay, because sometimes people say that, oh, this Taylor series allows you to cheat, because most complex problem can be simply approximated function approximation using Taylor series, but of course it has some disadvantages also. Okay. Okay, this is what I wrote in the previous slide. This understanding is important because we are going to define stuff based on gradient and Hessian. Okay. Yeah, the definition comes here. Okay. At a later point, we will come up with something called necessary condition and sufficient condition. They will say what your gradient and Hessian should take. Okay. For that, we will say your Hessian should be positive definite. This is a matrix terminology. Does any of you know what positive definiteness means? Yeah, it is given here also. So, if you take something like x is a vector, A a matrix, and then x is a vector here, okay, and you call this entire resultant as f. Okay. If f is greater than 0, okay, for this is important, for all x not equal to 0, okay, you cannot have x, all the x should be positive greater than 0, then this A is called positive definite. If the x condition is again not equal to 0, but if your f of x is greater than or equal to 0, greater than or equal to 0, then A is called positive semi definite. Okay. The same thing also holds good for Hessian. Okay. Of course, it does not matter, this is not also, it holds good for Hessian, because this is how we are writing the Hessian, this please relate these two, that is important. Okay. So, gradient of okay, this is just writing it that way. Okay. Del squared f, you can, if you take this, it is x squared. So, it will be 2ax, that is for the gradient, and if you do del squared f, it is just 2a. You understood what I am saying, right? This is nothing but ax squared. So, if you take a first order differentiation, it will be 2ax, that is what we write here. If you take a second order differentiation, it will be 2a, that is all. So, we will see where this positive definiteness and all that has come into picture. There is something called necessary condition and sufficient condition. Very simply and quickly put, what it means is, if someone wants to get into your department, okay, you set up some kind of an entry criteria, that is necessary condition. Okay. Just because you came to the interview, is there a guarantee that you will get selected? You are only called a interview candidate. You are not a successful candidate, you are only an interview candidate. Okay. But that is the entry criteria. So, but anyway, there are a lot of people who did not make the entry criteria. So, the necessary condition is the entry criteria, but there are multiple people, 100 people came, we selected only 12 people. One of you is, you are one of those 12, I am just giving some number. Okay. So, 100 people came, they were all candidates and we selected only 12 of you, because you are the ones who satisfied all and all the 100 satisfy those constraints first, but you only qualified to be the optimal combinations, right. So, necessary condition means it selects candidate points. Okay. You have already come up with this necessary condition and sufficiency condition, but you just do not know what, you did not relate them as necessary and sufficient, because when I told, have you have been introduced to minima and maxima earlier by saying f of x, then if you want to find the gradient, you take dou f by dou x. Okay. If you want to find the minima, what do you do? You do? No man, for finding minima, I give you a function and I ask you to find the minima, what will you do? What have you done in 12th standard? Positive definiteness, huh? Man, positive definiteness and all is engineering, right? You do not learn that in 10th or 12th, but in 10th or 12th itself you have done minima maxima. He is the honest guy, he says dou f by dou x equal to 0, that is what I will do, right. But then why do you do the second order?
Which point is maximum?
So, dou f by dou x equal to 0 is only a candidate. Okay. I have a function like this, here also dou f by dou x equal to 0, here also dou f by dou x equal. What does it say? The slope does not change, that is what it says. Okay. I give you a function like this, take our roads, pothole roads as, wherever it is flat, it is dou f by dou x equal to 0. So, all of them are candidate, but I do not know whether it is a hill or it is a valley, whether it is a peak or a valley, I do not know. Depending on whether you are maximizing or minimizing, I am interested in knowing whether it is a hill or a, that is when I am interested to see whether it is going this way or it is coming that way. So, for that and curvature of course, that is when I need to know my d squared information. So, your first order information is what your necessary condition is. So, you are a candidate, the peak is also a candidate, the valley is also a candidate. Okay. The curvature will tell me whether you qualified as a peak or a valley. Okay. That is all this is, but we will see how it is extended to n dimensions, that is all. Okay. So, the necessary condition for x to be a local minima, we already know this. Okay. I have written this for you, do not look at this, we have written, right. I have said, I would have written it in a slightly different way. I would have said f of x, f of x star should be, minimum means should be less than or equal to f of x for all x belonging to yes, this is what I would have written, right. Now, if I write it this way, if I take this f x star to the other side, I can write it like this, correct. I am just calling this difference as delta f, that is all. Now, what I am saying is, from Taylor series, because I do not know these values. These are all theoretically, any function you take this will hold good, this is only theorem. Now what I am saying is from Taylor series I can approximate this delta f, correct. Taylor series was that only. If you take this fx to this side, that is delta f, correct. So, this can be written as delta f equal to plus, okay, half is not required, fine, that is what we are doing here. Okay. So, I am just replacing this guy by a Taylor series expansion and I am saying it should be greater than 0, clear. This should be greater than 0, this is the idea, that is when it is minima. I am replacing this delta f by the Taylor series expansion and I am saying it should be greater than 0. What does this mean? What is the meaning of this? Okay. No, not global minima and all. What is the meaning of this is, see what happens is usually your d is very small, correct. You will not going to stand here and ask me what is on the outside of MSB what is the function value. You will ask me within this building, I mean within this room what is the function value there. So, d is usually small in terms of unit, in terms of percentage, right. So, d squared is going to be even smaller. Okay. So, usually this term does not dominate. Okay. So, it reduces, the order of domination reduces as you keep increasing your number of terms. So, we are not considering that at this point in time. So, we are only taking this guy. So, what does this say? There are only two quantities in the product, one is gradient of f, the other one is d. Can d be negative or positive? No, there is a point. You cannot say that you can always ask only on the positive side. I can also ask in the negative side. So, there is no way that I can say that, correct. Okay, that is one point. The other one is gradient of f. No, gradient of f, just do not jump into known solution. Is there a control on the gradient of f values? At the candidate point x star, that is derived from this. How do you know at the candidate point it will be 0? Did I say that it is a minima or maxima yet?
For it to be a maxima or minima.
Correct, that is derived from this. Okay. So, can d be equal to 0? It does not make sense. It can be 0. You can say, yeah, mathematically it can be 0, correct. But does it make sense? You are evaluating at the same point. So, you are going to drop means you are not dropping out of the equation. You are not considering d for the discussion anymore. So, the value that gradient of f takes becomes important. Okay. So, it can be positive, negative, that is, so the only thing that it can do for this equation to hold good. You cannot say gradient of f should be positive always, it can also be negative, right. So, in order for this inequality to hold good, gradient of f should be, this is what you already knew. You just did not know this in terms of gradient of f, you knew it in terms of dy by dx equal to 0. So, if you understand what dy by dx physically means is, it is flatness. Now, it is just flatness in multi-dimension, that is all. This is your necessary condition. Naturally, sufficiency condition is what? Second order business. In this equation, what is the second order business? You know this is to be equal to 0, that is what, sorry, that is what you just saw, this guy is equal to 0. So, for this equation to hold good, what you should do? Half d transpose d should be greater than or equal to 0, do not worry about half. D can be same story, D can be positive or negative, you do not have a control on that. Then what does it mean? H should be positive, definite or semi definite, it will take appropriate values, that is all. So, that is where positive definiteness came into picture. Now, you understand, we just use the terminology x transpose A x, now just replace that by this, that is all. So, then if your f is, meaning the outcome of this is greater than or equal to 0, then H is positive, semi definite or definite. If it is greater than 0, it is definite. If it is greater than or equal to 0, it is positive, semi definite, that is all. Okay. Okay. So, what this one says is, this is your I do not know, some chips are coming these days, right. Earlier we used to give the example of Pringle chips. You have seen the Pringles chips today, I mean yesterday or day before I saw on TV some chips are now coming in the same shape, but it is a packet. Have you seen the Pringle chips? Pringle chips is the classical example of saddle point used in control theory, optimization, any function approximation. Okay, it will be like this, just like a horse saddle. The point is, for this quantity, for this quantity and for this quantity, it is gradient equal to 0. The 3 points that I have marked here, the gradient is equal to 0. So, that is only candidate. It could be your minima, it could be your maxima, it could be a inflection point or a, what is an inflection point? This is an inflection point. You are here, you cannot say anything, you move this side, you will fall down, you go this side, you will go up. So, it is an inflection point, that is what this saddle point says, okay. That is all. This is very interesting because in what do you call like double well systems, classical example of double well system is if you go to these roadside dabas, okay, you are even, no, not in ours, if you see they will have table foot like this, on top of this the table will be there, okay. And either because of some issues in this one or on the surface in which it is landed, it will do like this, okay. So, it is stable in this end, it is stable in this end, it will not topple. So, that is a double well system, it is stable here, it is stable here, but in between it is unstable. So, it is a classical example of a double well system. So, these are classically discussed in multiple cases, not only in optimization theory, okay. That is the reason that I showed that. So, you do not have to worry about this necessary condition discussion, I am just going to skip this. It is the same idea, that is all I have done here, okay. Okay. So, there is a concept of Lagrange multipliers which we might not use a lot, but I will quickly go through it, okay. So, what it says is there is whatever we discussed, we have discussed constraint problems, yeah. So, usually we discuss only unconstrained problems first, and how do you solve constraint problem is you can actually reformulate the problem as your objective function plus something times your lambda times, that is what your Lagrange multiplier is, times your constraint, okay. Then it becomes an unconstrained problem. So, this information whatever I am going to tell you is something that you already know, which we discussed from our circle example, okay. That is the same stuff here, they are using a circle as an objective function and some straight line as a constraint, okay. So, if you see this might be much better than my pictures that I drew. So, this is my center, okay, this point here 1.5 comma 1.5, that is what the center is here, right. So, this is my center, and as I told the circle is expanding, okay. So, at this point the function value is 0.75 for this guy, for this inner circle it is 0.5, at this dot it was 0. So, it is expanding in that direction. Now, if you see this is your equation, but this is a slightly different one, it is an equality constraint, it is not an inequality constraint. So, what is the feasible domain in an equality constraint? On the line. So, what it means? It says you do not have buffer time, 8 o'clock means 8 o'clock, that is what it says, class starts equal to 8 o'clock, okay. So, you have to be there at 8, you do not have a grace time, it does not say less than or equal to 8.02 or 8.2. Okay. So, it is difficult sometimes, not most times, to satisfy an equality constraint, because in inequality constraint it is a domain. Here I mean if it is 2D it is a line, there it is an area, if it is 3D it is a surface, there it is a volume. So, it is much easier, volume means you have more space, right. So, now where will my optima lie? Obviously, it should lie on the line, okay, and then it touches. So, this keep on expanding and finally it touched here. Now, they are taking a simple feature here and saying, what they are saying is your in this particular direction your function is increasing in this direction, gradient of f, and your objective function or your constraint is going in that direction, which is gradient of h, gradient of f, they both are in the. So, that is a feature at the optimal point. So, there you can use it two ways. Here this is similar to what Kiran was trying to tell me, right, like del f equal to 0. You know that you can use it in the reverse fashion, or while trying to seek an optimal point you just need to see where my gradient and this guy are in the opposite direction, or if I have got in an approximate manner, if I have got my optimum point, I just need to check whether this condition holds good. Okay. So, the del f and del h will be in the opposite direction, proportional, they are not equal, they will be proportional, that is what this equation says. The constant of proportionality is your Lagrangian multiplier. Okay. This is a way to understand in optimization theory, but Lagrangian multiplier is used in different areas. Okay. One of my colleagues teaches parallel manipulator system dynamics, where they use Lagrangian multipliers. Okay. Computational geometry, they use Lagrangian multiplier. In one sense this is geometry, not computational geometry, but then in computational geometry also Lagrangian multiplier. So, in different contexts it is used. In the context of optimization, you can just imagine that they will be, not imagine, just imagine, visualize it, that your constraint and your objective functions are in opposite directions, but it need not be equal, okay, it is only proportional. Okay. So, yeah, so that is what it says, dou f, because that is your condition, right. So, if I rewrite your equation like this, if I call this guy as f, then if I want to find the minima, then I should say dou f by dou x equal to 0, that is what we are trying to do here. Okay. And that v or whatever lambda is your Lagrangian multiplier. So, you recast your problem using a Lagrangian function, then you come up with your necessary conditions. Yeah, this is the blindfold guy's example. Okay. Yeah, this is something that I will tell you, this will wrap up the optimization part, we will probably start a little bit on design of experiments. Okay. So, this is from a famous guy called van der Plots, he has a book on engineering optimization, he also runs this software company called Genesis. Okay. So, it is also called VR Nastran. VR stands for van der Plots. Okay. So, you can read this. This guy says, bet I can find the top of the hill. You can see that this guy is blindfolded. What this guy says is, you can try, but stay inside the fences. Okay. So, these are your objective function, these are isocontours. Okay. The green lines here are your isocontours, and this guy has a dog, but we can give him a stick in his hand, okay, so that he can find and then he can go up. Okay. So, what they are saying is, this is your constraint, that is what he is saying, these are your constraints, this is your feasible domain, make sure that you do not touch your fences because they are electrified, okay, you will get a shock. So, you will have to go in that. So, if you touch your fence you will have to come back, that is what it says. Okay. So, how will you go about? Objectives are what you are trying to achieve. What is it that I am trying to achieve? I am trying to go to the top of the hill. Constraints are what you cannot violate. What is that you cannot violate? The fences, I cannot go beyond the fences. The design variables are something that you can change. What is it that I can change? the direction in which I am traveling and the distance I am traveling in that particular direction. That is all I can do. So, any search based algorithms, they start with the initial guess, what we refer as the design point. Here you can call it as x naught. Now, you need to make two decisions. One is which direction. The direction is given by the gradient information. So, if you are going into a valley, you will go in the negative gradient and it is called the steepest descent. Now, if you are going to the hill, it will be called the steepest ascent. That is all. Positive gradient you need to look. Okay. You will transverse to achieve. Assuming the direction is known, I told you, right, will you jump 1 feet or will you jump 10 feet, okay. Is known, one need to know how much step size, that is your alpha naught, to travel in that direction. This alpha naught is kind of solved as a line search problem. It is very convenient because irrespective of n dimension, it will be solved into a one dimensional problem, okay. So, your next design point is simple, it will be x naught plus alpha times d naught. I need to go this much feet in that direction, that is all. So, this is achieved by gradient information and this is given by your step size calculation. It's a minimization problem. But so, this is how it works, it is just pictorial representation. You start from k minus 1, you can call this x naught, okay. Then this will be your x1, then this is alpha k dk, then you go to k plus 1, you go to k plus 2, you keep continuing like that, okay. So, this alpha is your line search, this d is your direction. So, please understand, only from here to here it is in this direction. When you went to that point, the direction is something else. So, let us say that you had a function something different here, okay. Your line search would have allowed you to go only up to here. Then you might have to go in this direction and then come in this direction, maybe, okay. Yeah. Let us not worry, these are interesting derivations, but I am going to skip all this is not required for us. Oh, this is about the steepest descent and yeah. So, for this one which took much longer than what I thought, okay, is if you want any references, you want to read a little bit more on these things, Aurora is the best book that you can pick up and read, okay. But the second book is a very interesting book. It is by Papalambros, he is from University of Michigan at Ann Arbor, okay. He gives it in a very nice fashion, okay. For instance, Aurora's book is very comprehensive, it is this big. I think it is about 650 rupees or 750 rupees, cheap editions are available. So is the case for Papalambros also, okay. Papalambros introduces the course in a design sense, okay. So, he does give details about the mathematics, but he introduces everything in a practical sense. So, it is a good book to hold for now and for later also, when you go work or go for a postdoc or something, it might be a good book for you to rely upon. So, it is a good idea to buy that book also, not too expensive. But these two give you a very good introduction, and also there are a lot of other books like Chandru Patla and Belagundu, okay. Ashok Belagundu from Penn State is a very good book, that is also a very good book, okay. And of course, our evergreen Kalyan Moideb is there, but that again that is also, he uses a different set of example problems. So, you can buy anything, I suggest these two, okay. Now, there are numerous books on introduction to optimization, okay, but these are the standard books that you might want to depend upon if you want to read a little bit more, okay.